Let's talk about the presentation on work and pressure and work, pressure, and what was the other one? Anyway, work and pressure. Okay, let's start with work. Work is force times distance. That's the definition of work from physics. So the units. Force, if you're in the metric system, a force is in Newton. And force is mass times acceleration. So we'd have to do mass times acceleration, and mass is usually in kilograms, and acceleration, if it's due to gravity, is 9.8 meters per second squared. That's if you're doing gravity. If you're doing something else, it would be whatever that acceleration is. But newtons is a force, the units for force. In the English system, a force is like pounds, weight. Now, some people think weight in the metric system is kilograms, and it's not. It's the mass. Mass doesn't change, but as you get higher up further away from an object that's creating the gravity, you get less weight, but your mass is the same. So there's the units for force. So what's the units for work? Well, if force is newtons in the metric system, and you're taking it times distance, you get newtons times meters, which was defined by James Joule as a joule, spelled Joule. Work in the English system would be force, pounds, times distance, which would be often done in feet. So it's often not written pounds times feet. It's often written foot dot pounds, or foot pound, maybe without the S, foot pound or foot pounds. Okay, so there's a little bit about the units. So it depends on whether we're working in the metric system or the English system. Now, let's do a couple work problems that don't require much, or at least one that doesn't require gravity to be involved. And so let's take a spring. And let's say right here, the length is the no stretching or compression, the natural length of the spring. Okay? So this is fastened to something. This is the natural length. So this is the position x equals 0, or x equals 0. Now, if you take a spring and compress it, the further you compress it, the harder it gets, and it's a linear relationship. So the force to compress it is just some constant times how far you've compressed it. And it's usually done with a negative k, they say, and k is then the spring constant. Similarly, if you want to stretch it, it's the spring constant times how far you've stretched it. Gives you the force. Force would be in newtons or in pounds, depending on which method you're using. So, if I have a spring that has a spring constant, let's say, of 0.5 pounds per inch, if I compress it an inch, it takes a half a pound to do it. To compress it 2 inches, it takes a full pound. Or to stretch it, same kind of thing. How much work is done compressing it to, let's say, compressing it 3 inches? Well, the force is changing. The force is going to be 0.5 times the x position. If I'm decreasing, it's going to be negative x times the make it a positive amount of work. The force is this, according to the equation, and we got to take force times distance, and we're going to use the distance in little chunks. We're going to push it a little bit, and I call that a distance, and that's going to be at some force, but then now we've compressed it, so now the force is increased, and so we're going to do the new force times a little distance, and then the new force times a little distance, and so we're going to add up all the forces times distance as x goes from 0 position to, I said, compress it 2.5 inches, 2 inches, let's compress it 3 inches. So this would be 0 to 3 of f times dx, 0.5 comes out, the integral of x is 1/2 x squared, and we have a half outside already that we're going to evaluate from 0 to 3. And if I put 3 in there, I get 9 times a quarter, so I get 9/4. Put 0 and I get 0, and so I get 9/4. The force would be in pounds, and it was times a distance, force times distance, and the distance was in feet, so we would call it a foot-pound of work. The work was in foot-pounds. 2.25 foot-pounds of work. If it was in the metric system and this was in newtons per meter or centimeter or whatever, then I would do similar and would be units in Newton meters or joules. So there's a work problem working with springs. Now I'm going to do another works problem that deals with, has some gravity involved. This is one I've done in class. Let's say we have a building here, and then there's a pulley out here, and a gentleman up here, or a lady, probably a lady because they're stronger than men, right? Anyway, pulling a rope that's hanging down to a bucket down here. Maybe it's got tar for roofing in it. And it's, I'll do this one in the metric system. It's 50 kilograms. And the rope has a mass of 0.5 kilograms per meter. And let's say the building is 10 meters tall. Now there's actually 3 ways to figure the answer out to this one. What you got to realize is as the person pulls some rope up, the 50 is still going to be there, but the rope is getting shorter, and so there's less mass, and so it's going to take less force to pull it. Now work is force times distance. So I'm going to call this length to the mass that's going to be shortening, getting shorter. I'm going to call it x. Now right at the beginning it's 10, but it's going to get shorter and shorter, and so the force that's going to be applied here. Or we're going to have 50 kilograms, but kilograms mass. To get mass into force, newtons, we have to take it times acceleration to gravity, 9.8. So 50 times 9.8 would be the newtons, the weight of the bucket. The weight is a force, plus the weight of the rope. So if only x of the rope is left, it's going to change here. So if x is the length that's still over, it's going to be x times 0.5. That would give the mass of the rope. Take the kilograms per meter times 0.5, and that would give you the mass, and I would have to take that times 9.8. That would create newtons. Kilograms times mass, or acceleration due to gravity, gives the force, a weight. So that's the weight of the rope, and that's the weight of the bucket. All the weight is a force times the distance I'm going to lift it. And I'm going to lift it a distance dx. In other words, I'm going to lift it a little bit, then the weight of the rope has changed, so I'm going to recalculate the weight and lift it a little bit. Oh, and then it's going to change, so I'm going to recalibrate this and lift it a little bit and recalibrate and then lift it a little bit and so on. So I'm going to add up all the work to lift it a little bit from and lifting it all the little bits that'll get us from 10 to 0, but let's just go the other way, 0 to 10, so we get a positive answer. So this is what we'd integrate. So for ease, just for understanding this, I'm going to change the 9.8 to 10 so you can understand a couple of ways to do this. 9.8 is close to 10, 9.8 is close to 10, so I'm just going to get an approximate answer here. So I'm going to get 50 times 10, 500 newtons, plus 0.5 times 10 is 5x newtons, times dx, integrated from 0 to 10. So 500 integrated is going to be 500x, and 5x integrated is going to be 5 halves x squared. And I'm going to integrate it from 0 to 10. And so I'm going to put 10 in, and I'm going to get 5,000 newtons. And I'm going to put 10 in here, and that 10 squared is 100 times 5 halves. Half of 100 is 50 times 5 is 250. And, Newton meters. This was Newton times x is meters. So we got Newton meters, and 250 Newton meters, which is a joule, minus putting zeros in there, which is going to be minus 0. So we're going to get 5,250 Newton meters, which is a joule. That much energy. That much work is done. Okay, now I could have gotten that answer another way. I could have said, I'm lifting 50 kilograms, which weight would be 500 newtons if I use 10 instead of 9.8. So I'm lifting 500 newtons, 10 meters. So that's 5,000 Newton meters or joules. That's this part. And then I'm lifting the rope, but that changes. However, I could think of the total mass of the rope. See, it's 10 meters long times that half a kilogram per meter. So 10 meters of a half, that's 5 kilograms of rope, times 10 for gravity makes it 50 newtons weight of rope. half of the rope has got to go less distance than the other half has to go longer distances, so they average out. So it's like the whole rope is just being lifted 5. So 500 newtons weight of rope could be just thought of all the rope piled up in the middle, lifted to the top, lifted 5. So it's 50 newtons, lifted 5 meters, which is 250 joules, which is this part, and it gets us the total amount of work that way. Now, the third possible interpretation of this didn't involve any calculus. This one will do calculus. Another way to look at this is to say, okay, I've got the 500 Newton bucket that I'm going to lift 10 meters. I've got 5,000 for that. That bucket's not changing going up, but the rope is changing. So now I'm going to say, okay, I'm going to take a small chunk of the rope, maybe a chunk that's dx long. Now if I take a dx long piece times the density, the linear density of the rope, I get 0.5 kilogram meters times this would be kilograms. 0.5 kilograms times dx gives you the kilograms. Take it times 9.8 and I get the newtons. And how far do I have to lift that piece? Well, that piece has got to be lifted x distance, so I'm going to take it times x, and then I'm going to think that one is at some x distance. There's another dx here, and all of this rope can be little dx's, and each one of them is going to be lifted some distance somewhere between 0 and 10 meters. Somewhere between 0 and 10 meters, I'm going to lift a dx piece. Dx times this would give its mass times the distance I'm lifting it. Well, 9.8, 10 times 0.5 is 5 x dx. Integrate that becomes 5 halves x squared. Evaluated from 0 to 10. Put 10 in there and they get 100. Divided by 2 is 50 times 5 is the 250. So, we can either talk about looking at this mass plus the mass of this that depends on the length times gravity, being lifted little bits at a time and adding up all those little bits as this gets less and less and add them up. So we can think about moving this up in little increments. Or the calculus the other way is to say we're going to lift that chunk and a little chunk there and a little chunk there and a little chunk. All these little chunks, we're going to lift them up to the top some x distance. The chunk at different x distances, lifting them to the top. And each chunk is dx long times the linear density gets the mass times 9.8 gets the weight of that piece is lifted x force times distance. Okay, I'm going to stop there with work and then I'm going to come back.